to talk for the next 20 minutes about the questions of how can we apply, let's say, considerations from resource theory to a specific instance of quantum and classical computation to somehow compare the energetic costs these two platforms would use to solve a specific computational problem. This is a joint work with my collaborator Hayata Yamasaki from the University of Tokyo. And before I get started, I quickly introduce myself. So the topic I'm mostly working on is the thermodynamics of timekeeping, which I'm very glad to have seen somehow during this week, especially also the poster session in the talk before, that more and more people start to care about how much does it cost thermodynamically to run some timekeeping device. And I'm working on this in the Markus Huber group at the Technical University of Vienna. And before I've studied at ETH Zurich, so two Alpine countries I've been to. So I'm glad to, for once, be in such a nice city. And my thanks also to the organizer for bringing together this great workshop. Yeah, some impressions on the right-hand side. And what I will talk about is this side quest I've been on for a couple of years now. That's the thermodynamics of computation. To motivate this initial question, we want to compare quickly, somehow from a practical perspective, the computational platform using quantum dynamics versus a classical platform. And somehow the intention we have is to make this comparison to show some achievable energetic cost for a quantum computer to solve a specific problem and compare this to a classical platform. And for the classical platform, we somehow want to think of a fundamental lower bound and try to figure out, is there some reason why a classical computational platform should have a non-zero lower bound on how much energy it consumes to solve a specific problem. And these notions of energy consumption and so on will, of course, more rigorously define as we move forward. So the structure for the talk is such that we'll start with recapping some computational basics. Especially, I want to explain to you what is an oracle and why do we use this in our setting. And then we move over to the thermodynamic and computational model, and then look at upper and lower bounds for classical quantum computation, and end with some concluding remarks. So one important ingredient I'll use for these considerations is an oracle, which comes up in computational complexity theory. And what an oracle does in the end of the day is it takes some input and maps it to an output, and we use an oracle if we don't specify somehow the internal dynamics of the oracle that produce these input-output relations. And one specific instantiation that I've looked at with Hayata in this project is Simon's problem. And you can think of this problem as a game. And the question we will look at is somehow how much energy do we consume to solve this specific problem. And to start this, let's say we think of this as a two-party game. I'll choose some end-to-end function f, and I will toss a $1 coin and have with 50% chance, I will choose that this function is bijective, and with the other 50% chance, I will choose this function to be a 2-to-1 mapping. More precisely, I choose a uniformly random bit string, which is not the 0-bit string, such that my function is invariant under an XOR operation of this bit string. Now, this sounds complicated, but somehow the thing that you should keep in mind is that I choose a random function. I don't tell you which function this is, and it's with 50% to 1-to-1 or a 2-to-1 function. And your task is to figure out which of these cases I chose. And I didn't tell you, what the coin toss did. And you try to figure this out with as few queries to me as possible. So you ask me x, I'll tell you f of x. And formally, this can be implemented with such an oracle operation, taking some input, x get 0, and it will map to x f of x. And one important point I will make already now is that there is no promise about what the oracle does on an input where y is not equal to 0, which implies that the inverse oracle is not necessarily accessible. I'll get to this point later on. And the computational model that you as the second party trying to solve this problem will have access to consists of some computer where you have a set of bit strings on which you can do unitary operation. In case you have a classical computer, you will do the Clifford set and only have diagonal density matrices. Now the oracle queries will be done with, can be modeled with a swap operation, and after, say, m queries, you will compute some output, swap this and measure the output, which will be your decision whether the function I've implemented is 1-to-1 or 2-to-1. Now, at the end, you have to erase whatever is left in the memory, and for this you use a thermal environment. Felix's talk from yesterday, I think, is a good illustration of how such a process will look like. So the thermodynamic model that describes this situation consists of these 5 parts. So the computation on the computer acts as a thermodynamic cycle. So we start and end in the same state, which means that all the energy exchanges have to sum up to a net 0. And we will define the energy consumption as all the energy that the agent that you would have to invest to do this computation, including energy exchanges with input and output system coming from the oracle queries. And due to energy conservation, these energy exchanges have to be equal to the heat dissipated into the environment. And now the main question that we do look at is, can we find some upper bound that is achievable for a quantum computer to solve this computational problem? And does there exist some fundamental non-zero lower bound for the classical computational platform? And ideally, we would have that the classical bound is greater than the quantum bound, showing that there exists in principle such an advantage. We start with the lower bound for classical computation, and there it's important to point out Bennett's uncomputing scheme, which might have come to your mind already, somehow proposing that whatever you compute reversibly, you can uncompute again, and therefore all the energy you've invested in the computation can be recovered, and there is not really the need for an irreversible erasure, and up to a order 1 correction from the output decision, there isn't a non-zero lower bound. Now, this argument doesn't really go through here because the oracle that I'm implementing is not necessarily invertible. And if the situation is shown such that me, who is implementing the oracle, uses a cryptographic primitive like a one-way permutation, for you using the classical computational platform, it will be computationally hard to invert that function. So you, with polynomial access, so with polynomial computational resources, you won't be able to invert this function and distinguish the pseudo-random function implemented from a truly random one. And under this assumption, you can't do uncomputation, which will lead to the only way out, then you have to erase whichever information you have gained from querying the oracle. And then we can use the equation for the energy consumption, lower bounded by the entropy that you have accumulated in your computer's memory, and ask the question, why does this have to be non-zero? And the reason for this is you don't really know the function, you just know whether it's 1-to-1 or 2-to-1. So the output state you get is an average over all possible functions compatible with the output decision. And this function, it turns out, for regardless whichever strategy you use to solve this classical computational problem, with success probability greater or equals than 2/3, the entropy is lower bounded by the input bit size n times 2 to the n, which is exponential in n. And if you run the numbers at room temperature, you find that for the 300-bit input, the energy consumption for the erasure only would be already more than the mass equivalent of the solar system. So yeah, so much for these numbers and the lower bound. Going towards the quantum case, we want to somehow switch gears and not ask about the fundamental lower bound, namely what is achievable. And for this, we have to make a decision of which energetic costs we to account for. So there exists in practice macroscopic costs for a quantum computation. So we'll have amplification, you have cryogenics, you even have the coffee machine in the office, and it's a question of which parts do you account for, which are necessary for solving that computational problem. But there are also microscopic costs, and these are the ones that we will focus on for these considerations. So whenever you do some gate operation U on your target system, the energy of that bit or set of qubits will change, and this is given by this expression. But as we've also figured out this week, unitary operations are not really for free. So if you want to implement some finite approximation to unitary operation, there's multiple models describing the required energy to do this. And one possible way is to use the result by Giulio Chiribella, Renner, and Yushang Yang, which says that for a fixed error of the unitary, the control cost that you need to implement this operation, this overhead cost, is of the order of the Hamiltonian divided by the error. But then the last contribution we account for is the reinitialization cost, meaning the heat that you dissipate into the environment for irreversible operations. Now you can sum all these contributions up. In the end, that's just the sum. We try to focus on the challenging part. So we sum the gate cost, we sum the energy exchanges with the input and the output, but this we can all bound by the size of the algorithm. So there is not really any surprise there. The two challenging components here are what happens with error correction if we want to have this computation fault tolerant at some finite error threshold, and erasure, as Felix told us yesterday, that perfect Landauer erasure is divergent in some Greek source cost or the other. Now it turns out error correction for a threshold, for a non-zero threshold, we can actually reduce the problem to erasure by using the scheme by Dorit Aharonov and others, where error correction at constant error is possible using only resetting qubits on the go, but not measurement. So we can really reduce these considerations to erasure, and this is the part that we will look at now. So you can understand this as an extension to the result that Felix presented. So I'll not have to explain luckily what erasure is again, but we want to map some arbitrary density matrix to well-defined ground state. Felix convinced us that this is infinitely expensive. We want to do it perfectly. So the question is here achievability. How can we achieve approximately such an erasure at some finite cost? And the questions we want to look at is somehow how many elementary gates do we have to perform? So it's the complexity of this task. What's the heat dissipation and the energy scales involved in all these operations? And going through this calculation, we select some fidelity below our error threshold that is non-zero, choose an environment at temperature beta, and we want to have that the heat dissipation into the environment is only eta far away from the Landauer bound. So what Felix told us about is this side of the inequality, and here we find some upper bound for an arbitrary small parameter eta, and the result that we get going through this calculation is that such an erasure is achievable in a number of steps t. These are the swaps that Felix talked about, that is proportional to the constant eta and epsilon. And what the relieving use that we see here is that all these scalings are polynomial or logarithmic, so we will never have an exponential blow up of this overhead coming from erasure. So we are on the safe side when we want to compare this to the classical energy consumption, which we saw was exponential. So summarizing all these costs for the quantum case, we had a sum of achievable gate cost, of achievable control cost, and of achievable initialization cost in the erasure, including fault tolerance. Now the question is, the quantum algorithm solving this Simon's problem how many gates and how many qubits does it require to solve this computational problem with high success probability. And it turns out that the computational advantage for this specific case can be translated with some polynomial overhead to an energetic advantage which is achievable. And the bound we found was n to the power of 8, including all error correction overheads, where n is the number of input qubits. So with this, we have already reached the end of these considerations, and I hope I'm still somewhat on time. And we summarize the messages that we learned here. And the first quest we looked at was, does there exist some fundamental lower bound for energy consumption of solving a specific computational problem? And the solution to solving this problem was introducing an oracle for finding settings where some operations are not invertible. And here we could use the cryptographic primitives implementing pseudo-random permutations, which are computationally hard to invert, and therefore Bennett's uncomputing scheme doesn't go through. So we can lower bound the classical energy consumption using Landauer's principle, which leads for Simon's problem to an exponential blow-up of the lower bound of energy consumption. And for the quantum computer, including error correction overheads and finite achievable Landauer erasure, we find that the achievable cost is given by some function of the polynomial function of the algorithm's volume, volume meaning width times depth of the algorithm times some constant, and those added up to separate the two costs. And with this, I'd like to thank for your attention. Here is some shameless advertisement for the work on the archive. Please feel free to check it out or send me an email if you have questions, feedback, or in particular also questions on the thermodynamics of timekeeping, which seems to become a hot topic here in this round as well. Thanks a lot.
Questions? So Simon's algorithm in principle has an exponential. So
yeah.
So there's this question: how much of an advantage do you have in terms of algorithm advantage? So the quantum computing is actually superior to classical computing. So one thing typically is argued in terms of the break-even time. So how long do you have to run a classical computer compared to a classical computer until it reaches the quantum? And one outcome is that quadratic speedup is not good. So it's just this will never be good enough to see the use of a quantum computer.
Yeah, this is what I have here. Yeah.
And you see that also from, can you give a thermodynamical argument how much the algorithmic advantage has to be before you're energetically more efficient?
So there are two sides to this inequality, and for one of these sides, we find explicit factors for the lower bound. Now, in terms of overheads that quantum computation has, I'm strongly convinced that there is a large range of n, which is somehow larger than this 50, 100, but somehow below 300, where the classical energy consumption blows up, and where the quantum computer would be advantageous in terms of energy consumption as defined here. Now, the precise break-even point would depend on the constant factors for the quantum platform, which, as I pointed out, would require to specifically look at the platform that you are using, and then this break-even point would lie somewhere in between. But indeed, I agree that there will be a range where, with respect to this figure of merit energy consumption, the classical computer would, of course, be more advantageous.
Yeah, I mean, it would be very nice to come with other arguments for quadratic or cubic speed up or so on.
Yeah, I mean, one thing we definitively see is that the computational speed up for Simon's problem is, I think, of order n to the power of 3. Now, if we or 4, I don't remember it precisely, but if we look at the overheads for error correction and finite lambda erasure, sum these up to give the energy consumption, we found a scaling of n to the power of n, which is significantly worse than this idealized computational speed up. Thanks for the question.
There are questions. Yes. And for 1 or 2 more if there are. Oh, good.
Hi, that's an interesting talk. Just a query about the cost of Mandel. So it looks like you accounted for this by looking at how the cost of initializing the memory. So we erase everything.
Yeah.
Now, in principle, this erasure can of course be done at some other environmental temperature. So how fundamental is this in the computational process? Because if we can erase it at a different environment, then obviously we can lower the energetic cost of doing that process. Or in some system where sort of this erasure process is more energetically efficient. We can always, perhaps, for example, using some Maxwell's Demon types, offload that memory, erase it in some other setting, and then couple it into our computation. So the question is there in principle a cost there, or can we in principle reduce it to 0?
I think you're touching upon a very important point here, and this this table I computed was for room temperature. So indeed, you could take this to 0 out. The question to reduce how physical is that we have an absolute 0 temperature environment at our disposal. But indeed, the question is like, what do we consider as somehow a fundamental, a fundamental constraint? And the arguments I gave before was that, or the question I put into the room was, can we find some fundamental lower bound on the efficiency of how we can implement reversible gates? And of course, in practice, I also agree that probably uncomputing will never be done, because in practice it just doesn't give you any advantage. But the question is this really a fundamental property of the platforms implementing these operations? And here I think that this question of what is fundamental is, do we somehow set in our setting a fundamentally non-zero temperature? And then if you fix some constant, the exponential blow up, it might give you some orders of magnitude, but it doesn't change the physics.
I guess my point is that there is the thermodynamics of the actual computation where we may need to do erasure during the computational process. But there's also the case where you can think about supplying the system with information batteries, which are pre-prepared in some ancillary site, which can be done without, at the time, without depending on what computation we should do. So if it's merely the initialization, then it's practically possible to consider sort of erasing, preparing these information batteries, in a very low-cost regime, and then bringing them in. But we need to separate that from, say, the erasure cost during a computation, whereby that is impossible to do because we can't wait an infinite amount of time to erase batteries at very low temperatures as we want to operate the computer in, say, 300 degrees Kelvin. Yeah. So it'd be good to distinguish these two notions of erasure.
Yeah, this would certainly be possible, but also such a battery. So we, in the setting, we decided to have the computation as a thermodynamically closed cycle. So if you include the battery, you would also have to make this cycle closed for a finite battery.
Bring those batteries to Siberia or something.
Yes. So, so as soon as you include this in the cycle, I don't think you could circumvent the argument, but maybe for a finite number of runs, you might be able to postpone this cost.
But obviously, you have to include these batteries. So it just means that you can now, in principle, erase them at a much lower temperature. That's too close.
Yeah.
Cool.
Yeah, thank you.
maybe that's a good point to wrap up. Both talks ending on the question of can we do something at lower temperature, defacing or erasure? Some food for thought over coffee. Let's thank Florian and Martin again.
Thanks.